It's good to be here talking to everybody. Today we're going to discuss TrueTest. First, I want to go over what is TrueTest, give some people an overview. Some of you I think are familiar a little bit with it. Maybe you've attended previous webinars, but I believe some of you are less familiar. Then we'll discuss some analysis options that TrueTest offers, and specifically focusing on flat panel displays and Mura, which is a common type of defect found in flat panel displays. Then we'll go over how to set up a sequence. This is a specific name that we use in TrueTest for a test plan or set of steps to perform the analysis on Mura and other defects. Then we'll get a chance to see TrueTest in action as it's going through and measuring some example flat panel display measurements we've already taken, and then a wrap up and Q&A, and that's our plan for today. All right, so what is TrueTest? TrueTest is a sequencing platform for automated production. So really it's a set of software tools and also our imaging colorimeter working together to measure devices under test, looking for defects or other analyses that we want to do. So TrueTest will work together with a hardware fixture or any other system that needs to be put into place for automated production to load the device. Then the device is told to show a pattern or otherwise change itself to adapt to what we want to show. The imaging colorimeter measures the device under test, provides the data to TrueTest, the raw data, which we then analyze using image processing and other techniques. And then we repeat. We send another pattern, measure the device again, analyze again, as many times as necessary to do all the tests that we want to do. So a little bit of overview of TrueTest, because we're going to be talking about it and showing it throughout this webinar. And I'm a software guy, and I can't help myself but explain some of the structure behind how TrueTest works. So there's a main engine that drives everything, but it's very modular. There are components that can be added and taken away from TrueTest as needed to help it fit into different automated production environments. Perhaps the only module that can't really be removed is the one managing the imaging colorimeter. That's the one in green on this slide. So this module just controls the colorimeter, communicates to it, gets the data back. You know, very, very basic stuff here. We also have modules to communicate to the devices under test, and that would be specific for every device. In the case of a flat panel display, it may be in various states of assembly. If it's fully assembled, we might be able to simply send DVI, HDMI signal to change patterns. If it's at different levels of assembly, we might need pattern generators to communicate to. Then we have analysis modules where we can perform specific tests for specific types of Mura, functional defects, general uniformity tests, really anything that is needed for the application. And there are many pre-packaged analyses already available, or they could be written even by customers. And finally, reports. So we need to get the data out. We have to send pass-fail information and generate a daily report on the results of the testing that was done. And all this can be controlled by a main user interface. So for the rest of this webinar, we're going to discuss the user interface that comes with TrueTest. And so since you're going to be seeing it in action and seeing some screenshots, I want to take a little bit of time to review what this interface looks like so it's not as unfamiliar to you. So this, you're seeing TrueTest now. The left-hand side of TrueTest is sort of the setup and control side, including the sequencing grid where we add and remove steps that we want to include in the sequence, as well as running it and canceling it if needed. And the bottom of that section is used for setting up the individual camera measurements that we're going to be taking. The upper right section is where we see all of the imagery coming from the camera and also the image processing that's being applied to it. And then below that is our analysis results window, where we see text-based results of pass-fail, numerical values of measurements, including luminance, chromaticity, numbers of defects, information about those defects, and so on. Okay, so there are some analysis options that we have, various actually. We have some point-based uniformity testing. Some of you may be familiar with taking luminance or chromaticity measurements, say with a spectrometer or spot meter. And there are many standards, ICDM and ANSI, just to name a couple, for measuring uniformity at 9, 13, or different numbers of points. And so we have a lot of these pre-programmed into the system. We can also search for functional defects. So these are things for LCDs and flat panels like lines, electronic issues, or pixel defects. We classify these a little bit differently from Mura, which we'll get to in a little bit, but they're defects nonetheless. And finally, the main focus of our webinar is on Mura. And that word kind of, some of you may be familiar with it and some may not. And I always get it a little bit wrong. I've heard that it's a Japanese word that is similar to blemish or bruise, and it really is a catch-all for various types of often glass defects or other subtle visual defects that are less obvious and harder to find than the functional defects. A common unit or a common way that we measure Mura is with something called JND, which stands for just noticeable difference. And the concept here is some humans will be able to see defects and others won't, but on average, is a defect just noticeable or not? So a JND value of 1, for instance, would be just noticeable, and a higher JND is more noticeable, and a lower JND value would be less or not noticeable. So there is a little trouble with Mura, as I've hinted at before. There's many different causes and flavors of it. Some of you may be familiar with this more than others. I think some of the names of the different Mura types vary from place to place, and again, there's not a very well-defined industry standard for the naming convention, but they all have different causes. For example, I've called out line Mura here. Maybe during the manufacturing process there was a roller or something else helping to put pressure or apply a film to the glass as it rolls across. Maybe there's a hitch in the system at a regular interval causing a line to appear where that roller was. Or maybe there's spot Mura where during handling or something the glass was squeezed or compressed, and that section caused a small failure in the glass spacers, and we end up getting this subtle spot Mura. There's all sorts of root causes and flavors. But the one common part of Mura is that it can feel very subjective. That is, different human testers, which is the classic way to find this type of defect, is human operators, that often human testers vary in their reports of, well, did I see the Mura? How bad was it? Where is it? All of these things are not as easy for a collection of human operators to do. As an example, some of you may start to see some Mura has appeared in our image here. A lot of people, I think, can spot the yellowish Mura towards the upper right, and depending on the contrast of your display that you're viewing this with, maybe you've spotted the other 3 Muras that had appeared in the presentation. Maybe not. I'll give you a little chance to to look at that and see what you can see. Again, Mura is a little bit difficult to detect, mainly because of the low contrast and the varying area and shapes and sizes. So actually the Mura examples on the screen are a good indication of the type of contrast and type of Mura that are difficult to find. All right. but it can be done. That's why we're here. So we can find the Mura. So this is an example of a flat panel display image that we've taken. It's actually set to black, so the LCD is showing a black pattern. This is in a grayscale from our imaging colorimeter on the left. And on the right is the final analyzed image. So I think in this case, the most obvious defects are along the left edge. When looking at the original image, you can spot some bright spots. In this case, the backlighting is along that left edge, and that's part of the issues there. What's a little bit harder to spot is maybe the Mura towards the center of the image. I think going back and forth between the analyzed image, which is a contrast image, and I'll get into that more later, it's sort of easier to spot going back and forth with the original image and that image. And then you can sort of see on the right-hand side some brighter areas that are highlighted by the analyzed image. And here, we have to set some settings to say, well, what's bright enough to be seen by a human observer versus our scientific camera instrument, and where do we draw the line? And so that's sort of the how our analyses are configured and work. So while Mura is difficult, it's not impossible. We just have to put our minds to it and get it done. So with that in mind, how do we set up a test sequence to actually find this sort of Mura? So now I want to get into more of the TrueTest interface and how we go about getting to this result. So the first step is to set up the measurement conditions. Specifically, what pattern or image are we going to show on the device under test? And again, we're going with flat panel display, and I'll choose some simple options to describe how this works, even if we don't use this particular option very much. For instance, a checkerboard pattern. In TrueTest, we define the pattern that we would like to use, and then, if needed, set up some properties of that pattern. In this case, we chose checkerboard as an example, chose the colors to use for the squares, white and black, and the grid size. Most common for looking for Mura is a simple solid color pattern, maybe a black state or a gray state or a white state, and also the various colors. But there are different options to look for different types of defects. So the next setup required is to set calibration and other settings for the imaging colorimeter itself. So now that we know what pattern we're going to measure, maybe we have to change the exposure time. If the display is very bright, we might need to adjust ND filters. If we want to capture color chromaticity, maybe we want to use our 3 color filter measurements instead of just 1 for luminance only. So we have to set up what settings the imaging colorimeter needs for that pattern. So once that's set up, we want to combine everything into a new step. So now we're going to show you how that step is added. So we actually add a new step. We then select the setup that we'd chosen. Previously was checkerboard, now we're just calling it the black pattern. Then we edit and find the measurement or analysis that we want to do. So there's a lot of different choices of analysis, and I'm just going to pick one, butterfly Mura. And then for that analysis, there are many properties that we can set. They come with defaults for how to perform the analysis. Most interesting is, of course, the pass-fail criteria. How do we define what passes and what fails? In this case, the default for pass-fail is any amount of Mura area is 0. We save our changes, and now we have a new step in the sequence. So for the rest of the webinar, I'm going to use, of course, pre-programmed steps that we've already set up. But that's how we go about creating our sequence. I also want to point out that you're seeing a lot of details of how this is set up, but in actual automated environment, of course, we don't want operators to be able to change everything. So there is an operator mode where there's only really one action the operator can take, which is the run sequence button. There are some menus to let them, for instance, choose a different sequence. Maybe you have different models of device you want to test. And so the software can be changed between the different models and then run a different sequence. But that's all the control that this mode allows. So now that we know a little bit about how it's set up and how it can work, let's see it in action. So here we're going to show a sequence. The upper right corner is going to show you the pattern that will be shown. And as the camera system measures, we collect the image data and start feeding it to image processing. So this is in real time. We're trying to do this as fast as we can. So the imaging process takes the measurement that's being shown in the upper right, and now the yellow sections are being analyzed. Red means it has failed. Green means that that step has passed. And white simply means we hadn't set any pass-fail criteria. It's just reporting the results. So I'm sure that went very fast. We're going to come back to this later. And also the next step is to sort of break down an individual analysis to sort of show you what's going on behind the scenes, even though in a production environment we want everything to go very quickly. So this single analysis, we're going to show you all the pre-processing that we need to do in order to find the Mura. The first step is to register where is the measurement inside the camera's field of view. So we find the corners of the display, we crop it and rotate it out, and you may now see that there's some cross-hatching or aliasing pattern between the CCD pixels and the display's pixels. We want to remove that. So we have an image processing routine that removes that crosshatch pattern for us, allowing us to find the defects on its own. You may start to see that there's a little line in this image, a little left of center. So this is what we call the reference image. This is sort of what the human eye is bad at seeing. Most flat panel displays have this 20 to 30% variation from center to corner. We want to find what that is and remove it. We want to compare the original measurement to this reference measurement. And that's how we can really pull out where is the Mura in the display. Simple point-to-point luminance comparison isn't enough. We need to figure out what the human eye is good at seeing, what it's not good at seeing. So this is the contrast image comparing the original image to the reference image, which makes it easier for our image processing routines to find that particular line and highlight it. And that's a lot of the pre-processing that we do in order to do the Mura. So this example was more of a functional defect, but the pre-processing of finding the edges of the display, removing any moire or aliasing if needed, finding this reference image of what the human eye is not so good at seeing and sort of discounting that and removing that from the image. All of that pre-processing is fundamental and used for all of the Mura detection steps that we use. So let's go back to the fast image again. So for each step, this is a real-time video of it in action. Each step in the sequence is doing the pre-processing. We're taking our measurement, finding the corners, cropping it out, removing any moire, and finding the reference image, and then comparing the original to that reference to produce this contrast image. And doing it all multi-threaded and as fast as possible. Because in production, speed is king. So just to highlight some specific types of Mura that we can find, I'm going to show you two images, actually of the same, two image processed images of the same display. So this analysis was looking specifically for edge Mura. And you can see, especially along the left, where we had the backlighting present, we see a lot of bright spots, and our image processing has found them and highlighted them and noted that there's a much stronger percent contrast change on that left side than any other side. But on each edge, there are still some areas of contrast highlighted by this test. You may also notice towards the middle, maybe bottom left of middle, there's a little bright spot there. This test was designed to ignore that center area and focus only on the edges. But in the next slide, what we will see is that we can design a test to find that center spot and not find the edge spots. So here we've run a blob analysis test looking across the image for any hot spots or dark spots. In this case, we focused on the bright spot, and we have configured it to ignore the edges, knowing that we have a separate test to look for Mura and other defects along the edges. So you've seen a lot of false color and a lot of contrast images. All these are just image processing techniques to help us pull out where is that Mura and what does it look like. All right. In summary, TrueTest is a platform that can help us sequence a number of tests in automated production. Each of those steps are configurable. You can change the pattern you want to show on the device, change the imaging colorimeter setup settings, and change the analysis that you'd like to do. There's various analysis options for uniformity, functional defects, and of course Mura. These options are extensible. So again, I can't help myself. Being a software guy, we have .NET DLLs that you can write. So customers can write it and make their own image processing routines, drop it into TrueTest, and have it be added as another available analysis to use. This could be used in R&D or production to look for these types of defects, or just create a general report of what's the behavior of this device. And actually, it's so flexible that TrueTest can be applied to more than just flat panel displays. Anything that an imaging colorimeter can take an image of and provide this imaging data for can be analyzed and sequenced for automated production. As an example, we could do some visual surface inspection of, say, the outside of a laptop or device, looking at plastics or metals for scratches, dings, dents, that sort of thing. So, we focused on Mura and flat panels here, but that's not all that is possible. Thank you all for your time.